On September 14, 2020, astronomer Jane Greaves stood before the Royal Astronomical Society in London and announced a discovery that should not have been possible. Her team had detected phosphine gas in the clouds of Venus, not trace amounts, but marginal detections at the edge of instrumental sensitivity. A concentration of 20 parts per billion, suspended 40 miles above the planet's surface, in a region where the temperature is 50 degrees Celsius and the atmospheric pressure is similar to Earth's at sea level. Phosphine is a simple molecule. 3 hydrogen atoms bonded to 1 phosphorus atom. But on Earth, it only appears in 2 contexts. Either it is manufactured industrially for semiconductors and fumigants, or it is produced by anaerobic bacteria, microorganisms that live in oxygen-free environments like swamps, marshes, and the intestines of animals. There is no known geological process that creates phosphine in planetary atmospheres. No volcanism, no lightning, no photochemical reaction driven by sunlight. Every model of atmospheric chemistry predicts that phosphine should not exist on Venus. It should be destroyed within seconds by the planet's sulfuric acid clouds, oxidized into phosphorus compounds that are stable and undetectable. But the signal was there. It's measured independently by 2 separate telescopes, confirmed across multiple observation runs. Spectroscopic absorption line at 266.94 GHz, exactly where phosphine absorbs millimeter wavelength radiation, which means one of 3 things. Either our understanding of Venus's atmospheric chemistry is fundamentally incomplete, or there is an unknown geological process producing phosphine at rates fast enough to replace what is being destroyed, or something alive is making it. And if life exists in the clouds of Venus, then biology is not confined to the surface of planets. It can thrive in the sky. Venus is not a mystery because we do not know what it looks like. Soviet Venera probes landed on its surface in the 1970s and 1980s, transmitting images of a hellscape, scorched volcanic plains, crushing atmospheric pressure 92 times that of Earth, and surface temperatures hot enough to melt lead. NASA's Magellan spacecraft mapped the entire planet with radar in the early 1990s, revealing vast highlands, lava flows, and impact craters barely eroded by the carbon dioxide atmosphere. The mystery is why Venus became hell when Earth became paradise. Because 4.5 billion years ago, Venus and Earth were twins. Similar size, similar composition, both formed from the same protoplanetary disk at nearly the same distance from the Sun. Early climate models suggest that Venus might have had liquid water oceans for the first 2 billion years of its existence. A habitable world where life could have emerged just as it did on Earth. But something went catastrophically wrong. The oceans evaporated. Water vapor, a greenhouse gas, trapped heat. The surface temperature soared. And in a runaway feedback loop, Venus transformed into the hottest planet in the solar system, hotter even than Mercury, despite being twice as far from the Sun. The water was lost to space, split apart by ultraviolet radiation, leaving behind a toxic atmosphere of carbon dioxide and sulfuric acid clouds. It's called a runaway greenhouse effect. And it is the nightmare scenario that climate scientists warn could happen on Earth if carbon dioxide levels rise too high, too fast. Venus is not just a failed planet. It is a preview of what happens when atmospheric chemistry spirals out of control. But in 2017, astronomers studying the habitability of exoplanets began to reconsider Venus. Not the surface, the clouds. Because at an altitude of 50 to 60 kilometers above Venus's surface, conditions are remarkably Earth-like. The temperature ranges from 0 to 50 degrees Celsius, the pressure is roughly 1 atmosphere, and the clouds are made of sulfuric acid droplets suspended in carbon dioxide, an environment that is corrosive but not immediately lethal. Astrobiologist David Grinspoon proposed that if life ever existed on Venus's surface billions of years ago, it might have retreated into the atmosphere as the planet heated, adapting to live in the clouds the way microbes on Earth live in the upper atmosphere, suspended in water droplets, drifting on wind currents. It was a speculative idea, till Jane Greaves detected phosphine. The discovery began in June 2017, when astronomer Jane Greaves at Cardiff University used the James Clerk, its Maxwell telescope in Hawaii, to observe Venus in millimeter wavelengths. She was not searching for life. She was conducting a survey of phosphine in the atmospheres of solar system planets, testing whether the molecule could serve as a biosignature, a chemical indicator of biological activity. Phosphine had already been detected in the atmospheres of Jupiter and Saturn, where it forms deep in the planet's interiors under extreme pressure and heat, then rises to the upper atmosphere through convection. This was expected. Gas giants have the energy and chemistry to produce phosphine naturally, but rocky planets like Earth, Mars, and Venus do not. Greaves pointed the telescope at Venus and scanned for the phosphine absorption line at 266.94 GHz. She expected to find nothing. Instead, she detected a signal. Faint but unmistakable. Dip in the spectrum exactly where phosphine should absorb radiation. She assumed it was an error. Instrument noise. Contamination from Earth's atmosphere. She did not publish. She did not announce. She spent 2 years checking the data, running models, consulting with atmospheric chemists to determine if there was any plausible way phosphine could exist on Venus without life. There was not. And then in 2019, she convinced her colleagues to observe Venus again. This time using the Atacama Large Millimeter Submillimeter Array in Chile ALMA, the most sensitive radio telescope array in the world. ALMA has 45 antennas working in unison, capable of detecting molecular signatures with unprecedented precision. If the phosphine signal was real, ALMA would confirm it. If it was noise, ALMA would see nothing. On multiple nights in 2019, ALMA observed Venus, and the phosphine signal appeared again. Same wavelength, same absorption strength. 20 parts per billion, consistent across both telescopes, separated by years and thousands of miles. This was the moment the discovery became undeniable, because instrumental errors do not replicate across different observatories using different technologies. If two independent telescopes detect the same molecule at the same concentration, the molecule is there. Jane Greaves and her team, including astrobiologist Sarah Seeger at MIT and planetary scientist David Clements at Imperial College London, spent months analyzing every possible non-biological explanation. They modeled lightning. Venus has lightning, and on Earth, laboratory experiments have shown that electrical discharges can produce trace amounts of phosphine from phosphorus-containing minerals. But the team calculated that even if Venus had 1,000 times more lightning than Earth, it would only produce 1/10,000th of the observed phosphine concentration. They modeled volcanic outgassing. Phosphorus exists in Venus's crust, and volcanic eruptions could theoretically release phosphine if the magma chemistry was exotic enough. But spectroscopic surveys of Venus's surface show no evidence of active volcanism on the scale required to sustain 20 parts per billion of phosphine in the atmosphere. They modeled meteor impacts. Meteorites contain phosphorus, and high-energy impacts could vaporize the element, potentially forming phosphine in the debris cloud. But the delivery rate of phosphorus from meteorites is far too low to account for the observed concentration. They modeled photochemistry. Ultraviolet light from the sun breaks apart molecules in Venus's upper atmosphere, creating reactive fragments that recombine in unpredictable ways. But every photochemical pathway they tested either failed to produce phosphine or produced it in amounts millions of times smaller than what was observed. Every natural explanation failed. Why does Venus contain a molecule that only life produces on Earth? Until now, this looked like a single anomalous detection, a chemical mystery. A molecule that existed in a place it should not, waiting for a clever atmospheric scientist to identify the obscure reaction pathway that explained it. But it was not waiting to be explained. Because in 2021, astronomers Ignace Snellen and Theres and Krenas independently reanalyzed archival data from the Infrared Telescope Facility in Hawaii and the Venus Express spacecraft's Virtus instrument, both of which had observed Venus years before Jane Greaves' discovery. They searched for phosphine at infrared wavelengths, a different part of the electromagnetic spectrum where the molecule should also produce detectable absorption features. They found nothing. No phosphine signal in the infrared. No confirmation of the molecule at altitudes where it should have been visible. This created a paradox. The James Clerk Maxwell Telescope and ALMA detected phosphine in millimeter wavelengths. But infrared observations, which should have been sensitive enough to detect the same molecule, saw no trace of it. Either the phosphine concentration varies with altitude in ways that existing atmospheric models cannot predict, or the molecule is confined to a narrow vertical layer in the clouds. Hidden from infrared detection, but visible to millimeter wavelength telescopes, this is the hidden barrier. The confirmation that should have validated the discovery instead revealed that phosphine's distribution on Venus is not uniform. It is localized, structured, as if something is producing it in specific regions and altitudes, creating pockets of phosphine that appear and disappear on timescales shorter than the atmospheric mixing time. And then in 2022, astronomer Geronimo Villanueva at NASA's Goddard Space Flight Center published a reanalysis of the ALMA data. Using updated calibration methods and more sophisticated signal processing algorithms, his team found that the original phosphine detection was contaminated by sulfur dioxide, a molecule far more abundant in Venus's atmosphere, which produces absorption features at frequencies very close to phosphine. Villanueva's analysis suggested that the phosphine signal might be an artifact, a misidentification. Sulfur dioxide masquerading as phosphine in the spectroscopic data. The discovery appeared to collapse, but Jane Greaves and her team responded with their own reanalysis. They demonstrated that sulfur dioxide contamination could not fully account for the observed signal, that even after correcting for sulfur dioxide absorption, a residual phosphine signature remained in the data. The concentration was lower than initially reported, closer to 1 to 4 parts per billion rather than 20, but still detectable, still unexplained. The debate became technical, spectroscopic, a battle over calibration techniques, baseline subtraction methods, and statistical significance thresholds. But underneath the technical arguments was a deeper question. Why were scientists so eager to dismiss the phosphine detection? Because accepting phosphine on Venus means accepting that we do not understand the planet's atmospheric chemistry. It means acknowledging that decades of models built on data from Soviet Venera probes and NASA orbiters are incomplete. It means admitting that Venus, the planet next door, the world we have studied longer than any other except Earth, is still hiding processes we have never observed. And if those processes are biological, it means life found a way to survive in one of the most hostile environments in the solar system, not on the surface. In the sky, floating in sulfuric acid droplets, metabolizing chemicals we have not identified, reproducing in ways we have not imagined. Why are we more willing to believe our models than our instruments? In 2023, NASA announced the selection of 2 missions to Venus, the first dedicated spacecraft to the planet in over 30 years. Veritas, the Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy mission will map the surface with radar to search for active volcanism and measure the composition of volcanic gases. And Da Vinci, the Deep Atmosphere of Venus investigation of noble gases, chemistry, and imaging mission, will drop a probe through the atmosphere, sampling the clouds directly, measuring their chemistry from the surface to 60 kilometers altitude. Da Vinci's probe will carry a mass spectrometer capable of detecting phosphine at concentrations as low as 1 part per trillion. If the molecule exists, Da Vinci will confirm it. If the original detection was an artifact, Da Vinci will find nothing. But the mission will not launch until 2029 at the earliest, and it will not reach Venus until 2031, which means for the next decade, the phosphine mystery will remain unresolved. A spectroscopic signal that divides the scientific community between those who believe it is real and those who insist it is noise. And then in 2024, astrobiologist Sarah Seeger published a study proposing a biochemical pathway that could produce phosphine in Venus's clouds. She suggested that if microbial life exists in the sulfuric acid droplets, it might reduce phosphate, a common phosphorus compound, into phosphine as a waste product of metabolism, the same way anaerobic bacteria on Earth produce phosphine in oxygen-free environments. Seeger's model required that Venusian microbes be fundamentally different from Earth life. They would need to tolerate sulfuric acid concentrations that would instantly dissolve terrestrial organisms. They would need to extract water from the tiny amounts present in Venus's atmosphere, less than 1% by volume. And they would need to neutralize the acidity inside their cells, creating a microscopic oasis of habitability in an otherwise lethal environment. None of this violated the laws of chemistry, but it required life to be far more adaptable than any organism discovered on Earth. It required biology to operate at extremes we have never observed. And the most compelling piece of evidence was not the phosphine itself. It was the pattern of its distribution. Because in 2024, Astronomer Rakesh Moghul at California State Polytechnic University reanalyzed data from the Pioneer Venus probe, a NASA spacecraft that descended through Venus's atmosphere in 1978. Decades before anyone was searching for biosignatures, Moghul's team found anomalies in the probe's mass spectrometry data, unexpected chemical signatures. It could not be explained by known atmospheric chemistry. One of those signatures was consistent with phosphine. Another was consistent with ammonia, a molecule that, like phosphine, should not exist in Venus's oxidizing atmosphere. Both molecules are produced by life on Earth. Both molecules are destroyed rapidly by sulfuric acid. And both molecules were detected in the same altitude range where Jane Greaves found phosphine in 2020. This was not confirmation, it was a pattern. A convergence of independent data sets separated by 42 years, all pointing to the same conclusion. Something in Venus's clouds is producing chemicals that do not belong there. On September 14, 2020, Jane Greaves announced the detection of phosphine in Venus's atmosphere. She did not know she was reigniting one of the oldest questions in astronomy. She thought she was reporting a chemical anomaly, a molecule that would eventually be explained by some exotic atmospheric process no one had thought to model. 4 years later, it has not been explained. Not by volcanism, not by lightning, not by photochemistry or meteor impacts or any geological mechanism ever observed on a rocky planet. The only process known to produce phosphine in planetary atmospheres at the concentrations observed is life. And the only way to rule out life is to go to Venus and sample the clouds directly, which we will. In 2031, when Da Vinci descends through the atmosphere and either confirms the phosphine signal or disproves it once and for all. But the deeper question is not whether life exists on Venus. It is what it means if it does. Because if biology can survive in sulfuric acid clouds, floating 40 miles above a surface hot enough to melt lead, then life is not fragile. It is relentless. It adapts to extremes we assumed were uninhabitable, finds niches in the sky and ice and radiation-soaked deserts, anywhere chemistry allows. And if life emerged independently on Venus, a planet that shares no liquid water with Earth, no surface habitability, no obvious connection to the conditions we assume are necessary for biology, then the universe is not hostile to life. It is saturated with it. Life is not the exception, it is the rule. And once you accept that life might exist in the clouds of the planet next door, the second rock from the sun, a world we have known about for all of human history, but only now thought to check for biosignatures, you start to realize how little we have actually searched. How many moons in the outer solar system have subsurface oceans we have never sampled? How many exoplanets have atmospheres filled with molecules we have dismissed as noise? And how many times have we detected evidence of life and explained it away because the implications were too destabilizing? Subscribe to Universe Uncovered, because the universe is not empty, it is chemical. And chemistry, given the right conditions, does not stay inert. It becomes biology, and we are only now learning to recognize it.